Seems everything's working. Yeah, exactly. I don't know what to do. This is a second lecture, right? There's this yeah, it's a sort of no, that's I need to find something to say next time. I have something to
Et puis, apparemment, c'est la critique de ça.
So welcome everyone. It's a pleasure today to have another session from Thibault Bonnemain. We're going to talk about the introduction to generalized hydrodynamics in integrable field theories. Right. So thank you. Thank you for being here. So this time I'll try to introduce the notion of GHD. In fact, the previous lectures, the first lecture I discussed statistical mechanics, the second lecture I discussed integral systems, and this time I'll try to introduce GHD, so the large scale hydrodynamics of integrable systems, and I'll do so through the prism of the KdV equation and its so-called Soliton gas. So I also introduce the notion of Soliton gas and the key techniques so you can come gas theory. So again, like last time, I'll start with a quick recap of last lecture. So last time I introduced the KdV equation as a prototypical example of an integrable nonlinear dispersive PDE. Okay, and I told you that it was an Hamiltonian system. So you can find a couple of Poisson bracket and Hamiltonians that generate KdV dynamics. And in fact, this is done by Hamiltonian, so this is a feature of integrable systems. And that means that this is not the only couple of Poisson bracket and Hamiltonian that yield the KdV equation. And this is important because it implies also that this equation features an infinite number of conservations. You have infinitely many functionally independent conserved quantities that all Poisson commute. And those the charges, the Q's here, they are all functionals of U and its derivative. So Q0 is integral of U, Q1 is integral of U square, and Q2 is the Hamiltonian there. Okay. And typically we express those charges in terms of their densities, the small q's. And since those charges are conserved in time, they also have associated space-conserved currents. So this big J is here, and the density of currents is related to the density of charges through this continuity or conservation equation here. And this will be the basis that we'll use to later construct the hydrodynamics of the KdV Soliton gas. Right. As I argued last time as well, integrability can have several meanings, right? And in the context of KdV in particular, it also means that it is solvable via the inverse scattering transform. And this comes from the fact that you can write the KdV equation as a compatibility condition for this linear overdetermined system where the Lax pair of operators, this L and M, here satisfies the Lax equation, provided that the potential U here satisfies the KdV equation. Okay. And we can use this property, we used it last time to construct the so-called Knoidal wave solution, which is the simplest periodic solution of the KdV equation. But in a more general setting, we can also use this property to construct multi-periodic solutions through the framework of finite gap theory that takes n-phase solution of KdV and associates it with a particular n-gap spectrum of the operator. Okay. And here's the endpoints of the band spectrum of this operator. They completely specify the solution of KDV up to an initial phase.
So what is the capital?
Capital N. N is the number of phases. It's a multi-dynamic solution. It has n phases.
What is the solution?
So you have a solution that is of this type. Theta 1, theta n, where all the thetas are solution phase, and you have that Fn of theta 1, theta j is equal to theta 1, theta j equals 5. Okay.
Do you read that n is determined by the KDV equation, or every n is possible?
No, every n is possible. Yeah, and every n is associated with a different spectrum. You have n gaps, n plus 1 bands, and depending on the size of the band, you have different phases here, different wave vector frequencies. Okay. More questions? Okay. And with this, we can also define n-Soliton solutions, and the way we do so is we take all of our bands and we all shrink them to points of discrete spectrum. Equivalently, it amounts to taking all our periods and sending them to efficient instead. Okay. And what's interesting with this kind of n-Soliton solution is first that well, any solution of the KDV equation, you can approximate them pretty well on a domain of size L that grows with m, so the number of Soliton solutions. So you can always approximate your n-phase solution by an n-Soliton solution on a domain that the size of which depends on the number of Solitons you put inside. And the other thing is that, as you can see here, those n-Soliton solutions, they asymptotically decompose into trains of well-separated solutons that you can clearly identify and that all move at constant speed. So in a way, asymptotically, you can map this kind of solution onto a system of free particles. And that's the basic idea we use to define a Soliton gas later on. Okay. So it's a bit of an oversimplification, but you can think of solutions to the KDV equation that are defined on the whole line as finite gap solutions and solutions that are decay quickly with space as n-Soliton solution. So that's probably the main difference. Right. So given this n-Soliton solution, what do we mean by Soliton gas? Last time, I ended the last lecture by showing you this picture. So this is a particular example of a 150 Soliton solution. Okay, and I showed you this to highlight the fact that solutions to the KDV equation can quickly become extremely complex. Okay, and that's even truer when you start considering real-life phenomena, because randomness can just through boundary conditions, for example, or from, let's say, the uncertainty you have when you are measuring your initial state. Okay. So here, what we mean by Soliton gas is a random solution to the KDV equation, but one which can be on a large, sufficiently large domain, described by a large ensemble of solutions. Okay. So to be a bit more specific, so let's say that this is not an n-Soliton solution. Let's say it's just a generic solution to the KDV equation. You can take a piece, a fluid cell of this solution, isolate it, and let it evolve. So let's say I take my gas again here, something like that. I cut it, then I have my fluid cell here. So this is UL. And since now I have vanishing boundary condition, I expect it to asymptotically decompose into well-segregated solutions. So I'm doing some sort of time-of-flight thought experiment here. Okay. And here, as you can see, every soliton here in my fluid cell is indexed by 2 parameters. So the first one, eta, is for the spectral parameter. So it characterizes the amplitude and the velocity of my soliton. It's constant in time. No two soliton can have the same eta. And the other one is called the impact parameter, this x plus minus here, and it represents the position the soliton would have actually for 0 if it did not interact with the others. Okay, this is linear superposition of soliton would hold at the time, which it does not, but let's pretend it does to give an interpretation to this. And what's nice here is that these n couples of spectral and impact parameters are enough to completely and uniquely specify UL at all time. Okay. So that's the main point here. Okay. And so what we mean by Soliton gas, by the Soliton ensemble I was talking about earlier, is all the n Soliton solutions that are initially supported on my interval size L, that asymptotically will decompose into trains of well-spaghetti solutons with given joint distribution of eta and x plus minus. Okay. And the Soliton gas is the limit n goes to infinity of this. Well, n goes to infinity of this. Right? Okay. Okay, so now we can ask ourselves, what about the thermodynamics of the Soliton gas? And even more, what about the large-scale dynamics, the hydrodynamics of Soliton gas? What does it look like? So this figure I've already gone over it twice already, so I'll be a bit quick, but we know that non-integral systems, they tend to thermalize, they relax to equilibrium, which is described by this Gibbs measure here. And then hydrodynamics is obtained under 2 main assumptions. The first one is that we can have separation of scales, that we can construct mesoscopic fluid cells that are locally at equilibrium, described by those parameters beta mu that vary slowly over the whole system, but are essentially constant over the mesoscopic scales. And then the other assumption is that those local equilibria will propagate in time. With that, we can construct the Euler hydrodynamic equation, which are but there's somewhat of a problem, because the Soliton gas here is supposed to represent a solution to the KdT equation, which is integral. And if you recall from last time, Fermi Pascal singles, they found out that integrability tends to impede thermalization. So they did not manage to observe equipartition of energy in the closed integrability system, which means that it doesn't relax to the same equilibrium. And then presumably it also means that this whole procedure should crumble afterwards. Right? But the thing is, we can construct Euler-type hydrodynamic equation for the Soliton gas. And in fact, it was initially done without relying on this local equilibrium propagation assumption. Okay? It's a bit technical, and it's something that I will talk about later, but roughly it amounts to taking a multi-scale expansion of modulated finite web solutions and then taking the Soliton includes. Okay. And on top of that, interestingly enough, through numerical simulation, it's been observed that even large M Soliton solution would eventually reach a statistically stationary state. Okay. So the main question here is how to characterize this as a stationary state if it's not a Gibbs one and if you don't have a partitional energy. Okay.
So sorry?
Yes.
Did you explain this form in last time?
Yes. Yeah.
The P is not integrable, right?
No, it's near integrability.
Yeah. From this integrable system.
Yes.
Non-integrable. FPU.
Yeah, exactly. So the thing is, FPU is very close to integrability, so it does thermalize, but extremely slowly. And when they did their initial simulations, they couldn't reach equilibrium.
Okay. Because
yeah. Because if you take FPUT and you look at long wave initial conditions, this is extremely well described by KDB. Yeah, sure. Okay. Okay, so how to characterize this stationary state? The thing is, the main ingredient in establishing the Gibbs measure are those three conservation laws. So the system conserves the number of particles, it conserves the momentum, it conserves the energy. But the thing is, here we are dealing with integrable systems. We have an infinite number of conserved quantities, so we need to find a way to account for those additional constraints. And a way you can do so is by simply, almost naively in a way, just adding more Lagrange parameters for all of your conserved quantities. And that's something that was first considered in quantum integrability at the end of the 2000s with great success. So, in fact, you can indeed construct some sort of statistical mechanics for integrable systems, and even more so, it may seem a bit paradoxical, but you also do have some form of ergodicity in integrability as well. So your system will explore the whole phase space. It's just that the phase space on your whole system is smaller than that of more generic systems. Okay, so instead of exploring the whole constant energy surface, you will explore the torus from the analytic theorem, but the trajectory of any initial phase point on this torus will be dense most of the way. Okay, so you still have this notion of ergodicity here as well.
All of the dimensional values spaces. Like 1D or
no, n the number of dimension. N dimension. So in the case of KDB, it's infinite dimensional. But it's the important part is it's half of the total available phase space. It's you have a regular variation of the phase space into invariant array.
I think that each invariant array is n-dimensional.
Yes. Yeah, each invariant array is n-dimensional.
But yeah, it's going to be n-dimensional.
Yeah, yeah, exactly.
Sure, inside each Do you fix all the beta dimensions?
You fix all the betas and mention the no, it's dimensional. Yeah.
So I think that this divided by space has x and p's. So maybe the p's.
Yeah. So in finite dimensional integral system, like you have a Hamiltonian system with a finite dimensional phase space.
I mean, it is very integral finite dimensional. Each coordinate is one given.
Exactly.
So it's one given.
Yeah, it's one given. Okay, if you are. Yeah, definitely. Okay.
So the vectorizity is inside each of these one pieces.
Yes.
So the different parameters that we use these are like equals.
Yeah.
Sorry, what is this like the one surface?
Because you have this conservation also constrain your motion of this surface. It's like when you have
But isn't the surface element or one surface element
yeah, and then
that's even depends on the rotation numbers.
yeah.
The rotation numbers are all incremental. It depends on this dimensional.
Yeah, so your dance on many dimensional. Yeah, okay, so you have n one the orbits and the source form of your dimensional close. So you say you have harmonic oscillator. So you have the energy you have around it. You have another particle, so you fix the unpurpled second orbit, so you have.
Okay, now I understand. So it's not just that you have the moments, but you also have other conservations.
Yeah.
The systems on top.
So here the system is coupled, but interoperability preserves this kind of structure. Questions? Okay, so this kind of ensembles that involve infinite number of Lagrange parameters, they're called the generalized Lipschitz ensembles, and the generalized aerodynamics, it describes the propagation of those local equilibria. So today I will be talking about this, how to construct the GGE for the KD equation, and then I will construct this generalized aerodynamics. Okay. Here's a quick recap slide. So we start with statistical thermodynamics, which is homogeneous and has only a finite number of conserved quantities, and from there we can either go to hydrodynamics, which keeps the number of conserved quantities finite but is homogeneous, or to GGEs, which is the opposite. You stay homogeneous, but you have infinite number of conserved quantities, and GHDs at the intersection of those two. Okay? And it features also results that are quantitatively and qualitatively different from the usual dynamics.
Sorry, we can also consider system with some extra new quantities, right?
Yes.
It doesn't have to be related to the position.
Yes. Okay. What do you mean?
I want to basically these things have been considered for the system with a general scheme.
Yeah. You can apply the general scheme. Yeah. Okay. So there will be some differences between the key thing here is that you have an infinite dimensional instead of having a system of n conservation rules, you have and so you go to a field degree instead, so you have some studies, but yeah. Yeah, but knows about it. Okay, so here's the outline of my lecture. So to start with, I'd like to talk about an old paper by Zaros from 1971. And the reason for this is that because it's here that the phrase Soliton gas appeared for the first time. Okay, and also it concerns itself with a very simplified version of the Soliton gas, and so it will allow me to introduce some of the key aspects. Then I introduce the thermodynamics of the KDB Soliton gas, and I do so by using some heuristic argument based on the fact that Soliton somewhat behave as classical particles. And from this, I will construct my equilibrium state, my GG. And then to lay ingredients to my heuristic approach, I then give you an alternative approach to derive some of the key results from the previous session, which does not require any heuristic argument or any other analogy between Soliton's particles, and which is purely based on finite theory. And finally, I'll put all of this together and construct the GHD of my Soliton gas. Okay, so the idea of the behind this paper, when he introduced the rarefied gas, was that he wanted to look into the statistical properties of large ensemble solitons and of integral systems in general. And in many ways, what he did here was some sort of proto-GHD. But the thing is that at that time, this type of research did not really catch on, and if you look at what papers cite this one, more than half of them have been published until 2017. To give you an idea. So people weren't really interested in that. Okay, but even that, what do we mean by that? So this corresponds to this corresponds to a solution of the KDB equations that can almost everywhere in time be approximated as a train of well-separated solution. And so this is generally only valid asymptotically, but here we're putting ourselves into a very particular regime in which it's always true. And here you want this kind of n-Soliton solution where the spectral and impact parameters are all distributed randomly. And what's interesting with this kind of solution is that interactions are very localized in time, and they almost surely do not involve more than two solitons at a time. Okay. So here's an example of a gas that is not quite rarefied. There's a bit too many solitons here, but it's nicer to look at something like that rather than very rarefied gas. Yeah, at least you can see things happening. And but what's interesting is also that even in this very simplified setting where your gas is rarefied, solitons can still exhibit some nice emergent behaviors. Okay. And it's even truer when the number of solitons n becomes large and the rarefied gas is the limit n goes to infinity as this. And to let me first start by introducing the spectral support gamma, which is a collection of bands. Yeah. So again, as I said earlier, the solution of KDB can be associated with a particular n-band spectrum, the n-band spectrum of the Lax operator. So here I'm considering a rarefied Soliton gas, so this should be associated with a collection of discrete points But ultimately, I would want to use this kind of formalism to also approximate more general solution that involve continuous spectrum. And I will do so by populating my bands of continuous spectrum with an increasingly large number of points. Okay. With that, I can also introduce my spectral density of states, and this is this gives me as a way to count solitons at time t in the vicinity of X with spectral parameters that are in the vicinity of eta. Okay. So here this has a clear meaning because in any region in which you want to count those solitons, you can clearly identify them, you can clearly count them, and they are well separated, so you can also clearly see the amplitude from which you can extract the spectral parameter. Yeah. Okay. So this is a density of solitons both in real and in spectral space. Yeah.
So also what you keep place is the edges of the lamps. So those are sort of place, and you calculate.
Yes. Yes. So here, the spectral support is the support from which the guitars can take values. Right. Yes.
So you don't have to take it like that. The real line.
Yeah, you can take the real line, of course. But here, the idea is to make it clear what type of solution you want to approximate. So let's say you want to approximate an n-phase solution, you take n, and then at least this way. And and this has some really practical applications that I will most likely discuss next time. But yeah. Okay. So this is a density in spectral and real space. So if you want to get the density of solitons, you have to integrate over eta, right? And that's also the way we define our right class. We want that this spatial density of soliton be small. Okay, and if you remember how I introduced this spectral support from before, we want this to be ideally to be smaller than gamma, which is the smallest value eta can take. And the reason for that is that the typical width of the soliton is 1 over eta. So we want them to be well separated. Okay. And I want to introduce this spectral flux density, and this counts the number of solitons that are passing through position x around time t and with spectral parameters that are around eta. Okay. So the density of states and the spectral flux, those are the objects that I will use to characterize my spectral gas from now on. Okay. And also like to know how those statistical properties would evolve at large scales. And the thing is, our solitons, they interact elastically, so the etas cannot change with the dynamics. So the system is said to be isospectral, and that means that the density of states can only be transported. Okay, you cannot create new etas, you cannot create new solitons. From which we can deduce that this relation between the density of states and the spectral flux. And the question here is now how to relate F to ρ. Okay. And naive people think that F should just be the density of states times the velocity of soliton or with spectral parameter eta, which is 4 eta squared. But in practice, it's a bit more complicated, in fact, because your soliton will move through the gas at its bare velocity 4 eta squared until it hits another soliton, in which it incurs a position shift. So that over large periods of time, over large distances, the effective average velocity of your Soliton can be approximated like that. So it's its air velocity modified to account for all the collisions it occurs as it moves through the gas. So this is the position shift, and this is the collision rate. Okay. And here's a small figure to illustrate this. So here I have a tracer solution that I send through a rarefied gas, and I compare its position after a while to that of a free Soliton with same velocity. You can see is that its effective velocity is a bit bigger than the free one. Okay. Right. So, of course, for all of those quantities to make sense, the variation must occur scales that are very large compared to the scales associated with the variation of the KDV wave field U. Right? But what those equations tell you is how the statistical properties of rarefied gas evolve of macroscopic scales. So those are the equivalent of the Euler equations, but for your gas. So those are for hydrodynamic equations. So the rest of the lecture will be dedicated to dense gases, to the thermodynamics, what the density of states means in this context, and also how to generalize this effective velocity to the case of dense gas. Okay. Chapter gamma is the spectral support.
Addressing, so the effective velocity doesn't appear.
No, because yes, that is true. So this is the case of the rarefied gas. And I'll tell you you go from one to the other. But this is you can easily get this thing from the usual effective velocity. You know what you can do is you just need to iterate one time your integral equation. So usually you would have the effective velocity here. You iterate this since you're at a low density. Yeah.
So the structure of the effective velocity is specific to the absolute solution of the equation.
No, it's not specific to it. So in GHD, the effective velocity will have this same structure as well.
But can you take back of the integral equation and the absolute solutions of those?
Yes.
What is the thing that changes?
It will be the position shift and the density. Right. Otherwise, it's pretty much the same. But yeah, the time KDV was the main integral system that was known as feature solutions. That's why that went with this one. Yeah, 71 is really early in the theory of integral systems. Okay. Okay, so I start talking about dense gases now, and to start with, I want to stress that the notion of density of states in dense gas is a priori not completely clear, because in a dense gas, your solutions are constantly overlapping and interacting with several others, and in a way, they kind of delocalize. Right, so to illustrate this, here's a short movie. So of course, this is not a gas, there's no randomness here, this is just a motion in short condition. But just looking at this, you cannot see the solutions. You cannot say how many there are, you cannot say where they are, and you cannot say which is amplitude. That this is something you can only know asymptotically once they are separated. Yes. And mean density of state when it comes to the dense gas is as a way to count the number of solitons with parameters in the vicinity of eta that would emerge from a given window asymptotically. So you take a piece of your gas, you get it above, and you count the statons that emerge. And insert the information, the density of states density. So even in the dense gas, in fact, the best way to look at the Soliton gas is through its asymptotic behavior, through its representation in terms of a train of well-separated solitons. Okay. And once again, I need to remind you that the eta, the spectral parameters, the Hippolyte parameter, they can play the role of action and of coordinates here. And knowing either the n-couple of eta and x minus or eta and x plus is enough to completely and uniquely specify your solution at all time. Okay. Right. So lastly, I want to mention is the relation between the x plus and x minus. I told you about this last time, but here let me remind you that the difference is just the sum of all the two-body scattering shifts the Soliton incurs as it interacts with every other from the gas. And what's interesting here is that even though in your dense gas your Soliton is constantly overlapping and interacting with several other, asymptotically at least, it looks as if it only interacted pairwise with every other Soliton and once. Okay. Right. Okay, so just before I go forward, I want to mention that it may look like I'm kind of repeating myself with this thing that in dense gas Solitons kind of delocalize and all of this is only asymptotic. And yes, in fact I am. And the reason for this is that it's still kind of an issue in Soliton theory. Okay, so here I will be discussing the thermodynamics and the eigendynamics of the solitons. But what I'm really ultimately interested in is statistical properties of the KDE wave field. Right? And okay, so the knowledge of the solitons and the Soliton content of the field should be enough to reconstruct the field and obtain the statistical properties. But in practice, this is also clear, and how to get the statistics of one in terms of the other is not really known. You can extract a lot of interesting information about the field, but if you want to get, for example, the PDF of the wave field in terms of the density of states, for now it's not known. So that's something I want you to keep in mind as I go through this, because this is only one part of the picture. Yeah. What do you mean by PDF? Full context statistics.
Probably dispersion functions. Oh.
Of you.
Yeah, but so the object, so quantities or
of the field itself. Like, yeah. So say you want all the moments of the field, for example. So currently this is not known. You can get we know how to get the first one because they come trivially when they are just the first two charge densities. But then, so if one is more, and then
maybe you say that you take one fluid cell and you observe some filter, of course you can take half a fluid cell,
yeah.
And you will obtain the same set of solitons essentially. It's just interesting. As if the solitons really were there, but they are not. You could obtain a completely different set of solitons. I think it should be like that in the periodic systems. So it's kind of not clear.
Yeah. No,
Pretty basic question. We're talking about asymptotic state.
Yeah.
We are also thinking about an initial state, which is stationary, TGE.
Yes.
In some case,
if you take your stationary state that is defined on the while, if you take a piece of this fluid cell of your solution gas and you isolate it from the rest, then you have certain energy and then you can compensate using the gas.
It's an artificial sense we are fostering concentration ionization. And you can create some other special treatment and see how people they see the appearance of the
Then you see.
so you can look at the translation environment.
Yeah, you never see solitons in practice. And that's why also I mentioned this thing regarding the statistics of the wave field compared to the results of solutions, right? Because that's what is important. It's I think in the end. But you have this. It's like doing a stochastic scattering transform. So we have one, we have the direct scattering with the spectral problem, then how to get back to the field itself. It's not clear. Okay. All right. Okay, so yes, let's say I pick a fluid cell, given that, of size L, I isolate it from the gas, and I can write on the very formal level its partition function as such, as a bar integral over all the incident solution, where here this is a generalized deep squared, which encodes all my conservation laws, it involves all my branch parameters, and here is an entropy term which is here to select only certain solutions that are initially supported on my interval of size L. Okay. And this, of course, we have to feed it on input. But this, at this point, it's a very formal expression because even with this entropy term, how do you define this measure for me? So it's not completely clear, but thankfully, as I told you earlier, the N-Soliton solution is completely specified by the n-couples of spectral and impact parameters, where we instead write this partition function in terms of those asymptotic coordinates. And this is what it looks like, and doing so is interesting because we are essentially mapping our N-Soliton solution to a system of n-free particles. Okay, so this makes our statistical mechanics approach more natural first, and also we can do this because the spectral parameters, the etas, and the impact parameters, the x minus, they are actually number coordinates, so the transformation is canonical and hence it's measure preserving. Okay. So now let me tell you a little bit more about those things. Here, this is a certain Baire velocity, so it's 4 eta square. The 2 pi here just here for convention. This is generalized Gibbs rate, so it's expressed in terms of those small W's where H here is a quantity of the charge Qm carried by a single soliton of spectral parameter eta, such that this of all the small W's is indexed with W. In the case of it's this H takes this very simple form, just eta is equal to k plus 1. And lastly, a constraint or an entropy term, which is here to ensure that your solution is initially supported on 0L. Okay, and this here is pretty important because it's something I forgot to mention. The seismic shift, here you can see the sign, which means here that the faster solitons are shifted forward, while the slower solitons are shifted backward. So effectively, solitons are repelling each other. So that means that in your given interval size N, you can put any number of Soliton with any special parameter you want, otherwise they don't fit. Okay, they rebel each other. So this is another important constraint. So what I'm doing here essentially is I'm counting all the possible Soliton solutions that are compatible both with those constant quantities and with these constraints that I need to be finite integral time equals 0. Okay. And the second part here is how to express this constraint on the field at t equals 0 in terms of the asymptotic parameters. Right? Yes.
Why are you having the P of beta and not so EP of
yes.
beta, not beta?
Okay. So yes, I could write just beta. This is I get this change of variable. Ultimately, it doesn't change anything on the thermodynamics. It's just a trick. I'll tell you later why. But for now, the idea is that okay, you have Solitons that move at a speed Fourier square, and I map them on a system of free particles, and so my particles move at Fourier square and integrate over the point. Okay.
But so this would give you some prefab, right?
Yeah, it gives you some prefab.
You can have some within the Fourier function.
Exactly.
So it's to get rid of that fancy
Okay. All right. Okay, so yeah, so the small part is this constraint, and for now, I'll give you some heuristic argument as to give you a way of computing this, and this is based on the fact that I will use this analogy between solitons and particles. So the idea that's why I assume that my solitons can be modeled as point particles that instantaneously jump when they collide with another one. Okay. So in other words, I assume that over a large scale, that the statistical level, the fact that my solitons have some width, and the fact that they don't interact instantaneously, this I assume doesn't matter. Okay, or that it only leads to some building corrections to my partition function. And I'll tell you later why I feel comfortable doing this, but this is my basic assumption here. Okay. And so this you can see also that as an extension of the collision rate ansatz of the rarefied gas. So I assume that I can still carry out the same kind of reasoning I carried out during this rarefied gas for endpoints. So then I would assume that all of my solitons are between 0 and L t equals 0, or eventually all my particles are between 0 and L. So this is to agree with my entropy constraint. And what's nice with KDE is that all the solitons have different special parameters, which all correspond to different positive velocity. Which means that asymptotically, my solitons are ordered. So they start ordered from fastest to slowest. Then they interact, and then they will eventually emerge again with order from slowest to fastest. Okay. And given that I can pick one of the soliton, let's assume that this soliton is the leftmost at t equals 0. So the idea here is to find a condition from the impact parameter so that all the solitons are initially in between 0 and L. So I take a soliton, I assume that at t equals 0, it is the leftmost. If it is the leftmost, it means that almost surely between this step and this step, it only incurred collisions from faster solitons. And it does not yet go up to the slower solitons, otherwise it wouldn't be the leftmost. Okay. So its initial position, okay, zero is is its specific position, so it's a parameter that I can't extract here because I assume it is physics. It is the leftmost. And then modify by all those directions it incurred from collision from faster solitons. And here there's a minus because, as I told you earlier, slower solitons are shifted backward. Now, also instead assume that it is the leftmost and not the rightmost and not the leftmost, and I can carry out some similar reasoning and say that okay, each opposition is its impact parameter plus all the shift from slower solitons, which are positive this time because yeah.
So the question is why the fastest one is the highest one?
Ah, okay, yeah. The specificity of KD solitons. So you see the amplitude is proportional to the density. You have an amplitude to the square and density for the square. Yeah, this is just special for KD. Right. So now you know that if you want your soliton to be between 0 and L equals 0, it must be between x left and x right, asymptotically. Well, in simple parameters, it must be between x left and x right. And you can take also the difference of equations, and from which, from this, you can define an asymptotic space Li as x right minus x left, and relate this asymptotic space to the real space. And this relation between the asymptotic and real space will give me a way to express my entropy constraint in the partition function later on. But just before I do so, I need to introduce a few more notions because ultimately we want to take the limit n goes to infinity of this. To do so, let me first introduce the small function Ln, which interpolates between the and I. I also introduce the function Kn as a ratio Ln, so the ratio of the asymptotic to the real space. So this here is just rewriting the previous identity.
And just to emphasize that the simple space depends on the solution.
Yes, yes. It depends on eta, yes. And then I take the constant dynamic limit, so I take both n and L to infinity, while keeping the ratios, the spatial density of solitons, kappa constant. And this equation becomes this one, where I introduced here the spatial density of state, and K, which is called the asymptotic space density. So here the density of state is constructed from the empirical density of spectral parameters. Right? So the spectral parameters are random variables, the empirical density is a random object, but in some large n limits, this becomes deterministic according to law of large numbers. And also here you can see that I multiply everything by kappa, which is the spatial density of state. Spatial density of solitons, which means that the spectral density of states is indeed the density of solitons paired with space and spatial space. Okay, as I defined it earlier. I can use it to count the number of solitons in a region of free space. I can also use it to compute the ensemble averages of the charge densities by integrating these H, which I recall as the amount of a charge carried by a single soliton over the density of state. Okay. So this is a rather natural definition. And as I will argue later, this density of state is completely determined by my Lagrange parameters, by the betas of my GGE. Also, gas is homogeneous. This asymptotic space density, it does also a natural interpretation in terms of a change of metric. Okay, so it relates the asymptotic space to the real space through this scattering sheets that dilutes the interval, the size of the interval, the Soliton's can be. Okay. Right. So this density of state here, it would be the, as I said earlier, so the name data I will be using to characterize my Soliton gas from now on. Okay. Right. Okay, so now let me go back to my partial function, which I have written here once again. So as I said, the small part is how to construct, to compute this constraint, but the thing is my previous construction. Yeah. Sorry. My previous construction gives you a way to do so. And, the quasi-particle picture is just amounts to a bounds on the integrating the impact parameters, because you know that for your Solitons to be between 0 and n equals 0, the impact parameters must be between x left and x right, which depend on the associated spectral parameter. So ultimately, what you end up with is just the product of all the asymptotic spaces of all your Solitons, which I can express in terms of my asymptotic space density. Putting all this together, here I put everything inside this exponential, and here again it gives weight and from here. This is the Jacobian from the change of variable from p to eta. This is the constraint, and this term comes from the Bonnemain factorials that are expressed using Stirling's formula and combined with this L to the n using the fact that n over n is gamma. Okay. Right. And once I have this, eventually I can also rewrite everything using the empirical density of states for finite this time, where this asymptotic space density depends also on the empirical density of states. Okay. Okay. So once I've written this, the large deviation principle tells me that I can approximate my partition function as such, where this f and f is conservatively between an energy function of which rho star, so the density of states of my Soliton gas at equilibrium is minimized. Right. So this, if you look at the previous slide and how the partition function look like, you can see this kind of as sort of an approximation. And this kind of work was pioneered by Bonnemain in the 60s, but if you want some more recent review on large deviation theory and how it applies to statistical mechanics, I would refer you to Schett's paper from 2009. And here, if you have energy functional, the first three terms here they are exactly the same as they were from the previous slide, but on top of this, you also have this rule of rho term, which corresponds to a configuration entropy. And this comes from Sanov theorem regarding the empirical density of spectral parameters. Again, that's because the spectral parameters are random variables, so the empirical density is a random object. And Sanov theorem roughly tells you that if you have an empirical density, let's say 15, x, then it tells you that the probability is that phi tilde is equal to phi at large n is exponential minus n over phi log x. Right. So that's where the rule good structure.
The probability of equality in the weak sense.
Yeah. Right. Then, utilization of this free energy function will give you this relation between K, rho, and the Gibbs weight. So this is somewhat analogous to the equation Bonnemain derived for the thermodynamic determinants of the big. Okay, and I'll tell you a little bit about this later. But here, what's important is that K is uniquely determined by rho through the asymptotic space relation, and then this in turns uniquely determined rho in terms of the values, so in terms of the betas of your GGT. So this specifies my equilibrium states. This specifies my GG. And then at this, using this utilization condition to evaluate the mean field free energy functional at the minimizer and eventually obtain the free energy spatial density, which takes a rather simple expression in terms of rho and k. Now, also, there's an opportunity to introduce the free energy density phase space, which is trait F, not by integrating over eta this time, over the spectral parameter this time, but instead over the momentum on my quantum particles. Okay. Right. So now I've specified the equilibrium states. So I will be able now to use the usual formulas of statistical mechanics to compute various thermodynamic quantities. But just before I do so, I want to tell you a little bit more about this Young equation. And I want also to introduce some alternative notations that are more generally used when it comes to GT. K is space. So it's in quantum thinking is the density of states. So it's one dressed. Yes. Yes. Yeah. Yeah. K is addressed. Yeah. Yeah. I come to this. So, but yeah, it's this is addressing relation. So, yeah, this minimization condition it can also be written like that. So this form is closer to the one derived by Bonnemain in the paper on the thermodynamic determinants, right? Where this epsilon is called the pseudo energy and it's directly related to K and rho. And here you have the free energy density in phase space, which can also be written in terms of epsilon. And here there is this name as flow energy through the fact that if you're dealing with a system with no interactions, then this integral part disappears. And if you're dealing also with a system which is not integrable, then the Gibbs weight simplifies and just becomes eta E. Okay, so the pseudo energy is a generalization of this quantity eta E, but to integrable systems that which interactions. And to make this clear, I can also define the occupation function by differentiating the free energy density with respect to the pseudo energy. And I end up with something that is reminiscent of a Maxwell-Boltzmann type statistics, except that the energy has been replaced by the pseudo energy here. And if you look at the form of epsilon, see that the occupation function is proportional to root over k, meaning that it's proportional to the density of states, the density of space, the density of solitons per phase error. So it's the density of solitons in real spectral space over the density of asymptotic space. So you can see this as an occupation function as a density of solitons within the asymptotic space. Okay, so this occupation function kind of makes sense. Right. Okay, so here, this, all of this is rather generic when it comes to the many original systems in GHD in general, right? So for all the integral systems in 1D, the normalization condition will always look like that. The only thing that will change is this scattering shift and the way the free energy density relates to the pseudo energy. So this form here, it comes from Savard's theorem, so it's really this set of classical particles that comes from the way we randomly distribute our spectral parameters. But if we, instead of solitons, we have, for example, Hermions of bosons, we would need to account for that. And ultimately, here we would end up with something that would be closer to a generalized Fermi-Dirac or a generalized Bose-Einstein. Okay, so here it might seem superfluous to have both F and N, since one is just zero positive zero, but in general, this is not the case. Right. With all this, as I said earlier, I specified my GGE, so I can use now those results to construct various thermodynamic quantities using the usual methods from statistical mechanics. And the first thing I can look at is entropy density of my solid gas. Sorry, I was about to take a break into slide or so. No, but it's good as well, so that's fine. Yeah, cool. Yes, it's not on the Teams. The lecture, it is on Teams. Yes. It's okay.
Let's try. No, this doesn't. Oh, maybe. Is it better?
Much better, yes.
Okay, thank you. Okay. So maybe it was the owl that for some reason didn't work well.
Okay.
It's always different. I don't know. It's,
Yeah, it's true.
it's a noisy, non-autonomous system. I don't know. So maybe we should. I stop this sharing.
Oh yeah.
Yes, it's like it's great.
Cool. Thank you. Alright. Yeah, but I think last time also there was an issue
With the owl, right? But
Yeah.
then there was this option about the spatial noise.
Okay.
That tweaking that it made it work. But this time we cannot.
Yeah.
So.
We'll see.
I can try. Can you hear as well now? Is it better? Maybe try yours from your.
Yeah. Can you hear me correctly?
I think it sounds pretty well good now. Now it's good.
Okay, great. Okay.
Awesome.
Yeah.
It was supposed to be. I have done this. Yeah, for me, the relation might be hit. Yeah, I did it all. Okay. Bad habits.
Sorry.
What do you plan to use for? How was your week? Think about these slides.
Did you work or did you?
And do you have the PowerPoint or PDF?
I want to
PDF. So perhaps that's really just before the talk, you send me the slides, and I can connect to that.
Evening, we ended it with the evening.
We'll just go to the
Or we can erase it also later, or we can also have it on a USB stick, because it's better if you use the PC in the room. If we try to use our own laptops, they usually allow issues with connecting online. So you can either send the slides to me, or if you have a USB stick, that would be great. Thank you.
Oh, yeah, yesterday it needed.
No, it was inside.
Inside freezing. Yes. Wow. You were ready to go out to play.
Yeah, like, so they had 3 sessions per week, but they were outside and one had inside, and only going to one inside, which is just about because I can't keep there because friends involved and it's always on Wednesdays. I know at that. But then, yeah, I mean, like, if I have the option to keep like going outside
Yes. So yeah. Solution.
It was a big part. I mean, it wasn't
and also, it was just
not live, but anyway.
because in other yeah. Yes, I had it
Well, yeah, but yeah.
less
l'énergie, ce serait c'est beaucoup moins
So in nature, the nature is
Par exemple, si tu prends des particules, tu peux imaginer que ça fait ton issue initiale de manière que je fais radical.
C'est un peu comme ce que je parlais de conversation, tu vois, quand tu essaies de définir tu définis quelles conditions initiales sont admises. Et maintenant, tu veux éviter les conditions initiales qui amènent des forces infinies, parce que tu peux avec une problématique de particules dans une donc, comme tu restes sur des GG, tu vas avoir ouais, un truc pas bon.
Ok, toute la mission initiale, quand il était 0 par rapport à J, il y a naturel, tous les oscillateurs, aussi en phase, par exemple.
Ouais, non, ça c'est la diction. Voilà, c'est ça. C'est ça.
Perhaps we should continue.
I mean, obviously, you know, it's just nature, it's not in storing.
Okay, so let's start again then. So yeah, I just characterized my GG, so my statistical equilibrium, and using those this previous construction, I will now show you how to compute some statistical, thermodynamic quantities. The first one I want to look at is the entropy density of my Soliton gas. And from traditional statistical mechanics, I know that the entropy should be related both to the Gibbs weight and to the free energy, except that traditionally this W should be beta times the density of the energy. But here, in an integral system, I need to take into account all of my conservation laws of my Lagrange parameters, and I do so by taking the density of the Gibbs weight, so the small w integrated over the density of states. And using the previous expression I derived for the free energy density, I obtain a rather simple expression for the entropy as well. Okay. Now, using this, I can also compute the ensemble averages of my charge densities by differentiating the free energy with respect to the associated Lagrange parameter. And this will be slightly more technical, but ultimately the result will be fairly natural. And to do so, let me first recall the expression for the free energy density in phase space, and the occupation function. And as you can see here, from this relation, the subtle part here is how to obtain the beta derivative of the pseudo energy Lc. So to do so, I'll take a closer look now at the Yang-Yang equation, which I can differentiate. And here, note that this W is sum of the beta H. So differentiating with respect to beta amounts to selecting a particular charge H. And this brings me to define this dressing operation so that the beta n derivative of epsilon is just H dressed. Okay? And here the dress function, they solve a Fredholm equation of the second kind. So it's something we don't always know how to solve analytically, but still this type of equation is well known. There are lots of results about say the convergence of the equation or how to find a approximate solution. And this operation is very important in GHD. In fact, many as we see, many key results can be expressed in terms of dress quantity. Here I've written it in a fairly generic way. See where I put a generic space shift for which is this one for KDV. So again, this is something that is generically present in GHD. Okay. And, in fact, we've already encountered an example of dressing, so that's what we were talking about earlier, Paula. So if you take the definition of the asymptotic density of space, multiply everything by eta, and use the fact that n and rho and k are related, you end up with this equation from which you can identify that eta k is just eta dressed, or h not dressed, or the beta not derivative of the pseudo energy. And one last thing I want to mention before I finish this quick aside on the dressing operation is to introduce one of the many useful property of the dressing operation. And this allows me to express an integral that involves one dress quantity into a second integral that involves a different dress quantity that may be more convenient to compute. And that is what I will use now to simplify my ensemble averages. I go back to my averages. Now I have a way of expressing this derivative of epsilon in terms of dressed quantity. So it's just Hn dressed. Then I use the property of the dressing I told you about. So initially I had H dressed. I put the dressing on the P prime here, and yet then using the previous identities I showed you, I finally end up with the fact that the ensemble average of the charge density is just the charge carried by a single Soliton integrated over the density of states. So this is a very natural result, and this may seem to be a rather roundabout way of obtaining a result we already knew about, right? But at the same time, we also make sure that things were consistent. Okay. And here are a few examples of those charge densities. So as you can see here, the first two are particularly interesting because they are the first two moments of the field, right? And so in a way, with this construction, you directly get the average and the variance in the field for free. But afterwards, the charge densities become more and more complicated. They start to involve the x derivatives in the field, and so getting the moments of the field from just this construction becomes tricky. Okay. So U is the KDV wave field. So probably that you can construct other moments by combining some charge densities, but it's not completely clear a priori how to do so. Okay. Perhaps more interestingly, we can also compute the static covariance matrix, so which is the integrated connected correlation function here. obtained by differentiating twice the free energy density. Okay. And again, using another nice identity involving the dressing, we end up with this fairly compact expression, which again involves dressed charges as well as the density of states. But on top of this time you have the theta function, which is called the statistical factor, which includes the statistics of your particles. So here, since our solitons follow a Maxwell-Boltzmann type statistics, the statistical factor is trivial, but it's not the case in general. And this, again, we expect this formula to hold very, very generically when it comes to many-body interval systems. So, provided that you know the phase shift, spectral support, and the statistics, in which case you wouldn't know it. Okay. All right. So, okay. So this is nice, but at this point, this is still fairly formal, especially if you consider that to get this quantity, you need to integrate over addressed quantities, right? And so what you may ask is, what do we gain from doing this? And the thing is, if you want to compute correlations for Soliton gases, let's say by doing ensemble averages of several realization of a Soliton gas with a given density of states, this can literally take days. In fact, it's already highly non-trivial to generate 100 Soliton solutions. So that's something we'll be talking a little bit about next time. But here, this kind of Fredholm integral equation, maybe you don't know how to solve it analytically, but numerically it's very easy. It can be done in a few seconds on a mid-range laptop. Okay? So you can see this thing here as a powerful computational tool. And in fact, that's what we computed when we decided we wanted to check that our construction was correct and if our assumption that solitons behave as classical particles was legitimate. We decided to compute the first 3 entries of the static covariant matrix by averaging over many realization of 150 Soliton solutions, which parameters were distributed according to 3 distinct densities of states. And then we compared this to the GHD prediction. And here this MB column, so for MB for Maxwell-Boltzmann, correspond to exactly this expression with theta is equal to 1. And just in case, we also checked, we also computed it for different thetas corresponding to Fermi-Dirac cosine time to see if maybe our basic hypothesis was maybe wrong. And we can see here that the Maxwell-Boltzmann column agrees very well with the simulation. So here I've introduced the density of state of my Soliton gas. I've related it to the GGE of KDV. So now I should have enough to construct the GHD of my Soliton gas. But just before I do so, I want to tell you about an alternative approach that doesn't involve any heuristic argument and that doesn't require the analogy between solitons and particles. And so the next section will be a bit more technical, right? So I'll try to keep it short and to give you only the broad strokes. But this is for those of you that want to know about a more rigorous approach. And
indeed, I think so. This formula there for KDV Soliton gas, I think there is no other way currently based on ISP or anything to actually derive that formula.
Yes. And that's the thing, because at this point you can ask yourself, why go through the heuristic argument at all if we had this alternative approach which is more rigorous. And the thing is, this one is really less technical and it's still widely applicable, and you have other problem interferences.
Why is not triggered?
Because you are assuming that your solitons behave as classical particles, that you forgetting that they have width and yeah. So you have some issues here. You have some heuristic arguments. But in fact, you can take this and use it to characterize some different topological systems like Boost situation. And for this, the method I will talk about in the next section, it doesn't exist for business. People don't know how to do it. So it's nice that we have a simple, widely applicable approach still. And the other thing is that it gives you a nice interpretation of what's going on in terms of shifts and dilation of the available space, which is not clear from the other approach involving finite theory. Okay. Right. So yeah, okay. So it's been known for a while now that the n-phase solution of KTV, which is associated with a particular n-gap spectrum of the wax operator, can be written in this way, right? Where lambda and phi here are constants of extensions that depends on the endpoints of the band spectrum. Where this is the Riemann theta function. This theta here is called the phase vector, and it's what encodes the XMT dependence of your KV solution. And here B is the n by n Riemann period matrix. Okay, so it's a special function. I don't remember exactly the expression.
Special.
Yeah, it's a special function. It's you can write it in terms of sums of exponential of, I don't remember exactly why, but yeah. Okay. Right. So this also you can see it a bit like it can be a bit reminiscent of the tau function from Madison I introduced last time, because you still have this second log derivative. Yeah. In fact, if you take the Soliton limits, the first two constants cancel each other, and the theta function just gives you the tau function we introduced last time. Right. So now I'll give you ways to evaluate all of this lambda, phi, theta, and b. But to do so, I need first to introduce the two-sheeted hyperelliptic Riemann surface R, which is defined by this polynomial here, whose roots are just the endpoints of the bands. Okay? And on top of this, I will also need to introduce a canonical basis of cycles on this Riemann surface. So here you have an example for n equals 4. The A cycles surround the bands, and the B's are their canonical conjugates. So B1 surrounds all the gaps, B2 surrounds all the gaps except the first one. Okay. And the last ingredient I need is a basis of meromorphic differentials on R, phi here, that are determined by the normalization condition here over the A cycles. So now I have all the ingredients I need to evaluate lambda, phi, theta, and b. First, lambda is just the sum of all the endpoints of the bands. Phi, it can be expressed in terms of the sum of integrals over the A cycles. The Riemann period matrix instead, it's integrals over the B cycles. And the phase vector, it just takes this very generic expression, kx plus kt plus initial phase. Right. And of course here, the choice of the initial phase is free, but the choice of the wave vector and the frequencies, the k's and the omegas, is not. They depend on the spectrum. Okay. And they depend on the spectrum and on each other through the so-called nonlinear dispersion relations that I've written here, which involve the Riemann period matrix. It involves the constant lambda, and it involves this vector C, which is constructed from the normalization coefficients for the meromorphic differential style. Okay. So those are complicated objects, right? But they are the main ingredients of the basis of the Soliton gap theory. And in fact, that's what I will use to define the density of states and the spectral flux density later on. Right. So just to briefly recap what I just said, if you need to remember just one thing from what I just said, is that formally you can write the n-phase solution of KDV as such, where the x and t dependence only enters through the phase theta here, and where the wave numbers and frequencies only depend on the endpoints. And in fact, you can see this kind of as a nonlinear generalization of a Fourier series. So instead of having a linear superposition of plane waves, you have a nonlinear superposition of cnoidal waves, okay, which is the basic solution of the KDV equation. And in fact, if you take the small amplitude unit of such a KDV, if you put a parameter in front of the nonlinearity, send it to 0, this just gives you plane waves, and the nonlinear dispersion relation just gives you a regular dispersion relation of linear waves. So this limit here is a limit of the theta function. So the function is generalization of this.
So you get doubly periodic functions here. So, no, the Cn function is doubly periodic, no?
No, Cn is not.
No.
Cn is not. Yeah, Cn has one gap. 2 bands, 1 gap. So you have a semi-infinite band which corresponds to a background vacuum. Okay. Okay, so yeah, now the main question is, given all that, how to construct a gas and what should be its nonlinear dispersion relations. Okay. So to do so, the first thing it's natural to look at is solitonic limits. You take all your bands and you all collapse them to points. So you can introduce the spectral parameter eta like that, and then take this limit for all the endpoints of the bands. And if you do so, what you get is not really a Soliton gas, because essentially you have zero density over the whole line. So you can see because here all the wave numbers go to 0 if you take this limit. So to keep things interesting, we want to take the Solitonic limit, but at the same time, we want to increase the number of phases so as to keep the density finite. So we want all the wave numbers to go to 0 while keeping this quantity finite. And this makes sense because k being a wave number, this quantity has a natural interpretation in terms of average density of waves per unit length. Similarly, this being frequency, this is a flux. Okay, and of course, because of the nonlinear dispersion relation, fixing one implies fixing the other as well. So this procedure is called the thermodynamic spectral limit, and it's obtained under a very specific scaling of the bands and the gaps. So to keep finite density, you want the gaps to go as 1 over n, and you want the size of the bands to be exponentially small with n. Okay. And now, under this scaling, we can take a closer look at the nonlinear dispersion relations, okay, which I recall here. And then I will make my scaling a bit more specific by introducing the Smooth function kappa and nu, which interpolates between the k's and the omegas. I will also introduce the function psi, which is the density of bands, and tau, which is the logarithmic bandwidth. Putting all of this together, I can express every terms of the nonlinear dispersion relation under this scaling. So the expressions, and in particular, I want to show this because interestingly, we naturally see appear the Soliton scattering shift here from the Riemann-Poiseuille matrix. But putting all of this together, we finally get the asymptotic behavior of the nonlinear dispersion relations, which, given the logarithmic bandwidth tau, specifies the wave numbers and the frequencies through kappa and yeah, 5 minutes. Yeah, I'll just finish this quickly. So finally, I want to take the continuum limit. To do so, I will introduce the spectral density of states here as a product of kappa xi, so the product of the normalized wave number times the density of bands, such that the sum over the wave numbers becomes an interval over rho. Right? And in this case, rho is indeed the density of Solitons per spectral and spectral length and real length. Okay, so as I introduced it earlier, I can also introduce the spectral flux density in a similar way, except that it plays this role but for omega instead of k. Okay. In doing so, I obtain this thermodynamic nonlinear dispersion relation where I've introduced one last function, sigma, the spectral scaling function, which encodes all the important properties of the large spectrum in the thermodynamic unit. So that's what I end up with. And as you can see, rho and f, they both solve a Fredholm equation of the second kind, which both involve the scattering shift. And in fact, those are examples of dress operations. So you can see this first equation adjusts the definition of the asymptotic space density that we obtained from our heuristic argument, but which is there derived from a completely different approach. This is just the dressing of rho eta cube, and through this identification, we can also notice that sigma is nothing but the inverse of the occupation function. Right. So maybe I'll stop here. And, yeah, we'll finish later. We'll do GHD later. Right. Yeah, go ahead. Of course.
Now, so you made the relation with the free particle.
Yeah.
And in that case, there's no straight line included, I suppose, in the free particle. But there is still some kind of interaction which one can take. Find still waves and all that. So surely you can do something like that also in integral phase.
Yes. Yes.
Do you know how to do that or not?
Okay. To understand what you mean, is it with respect to KDV or in more general?
KDV.
Okay, so what do you mean by this?
So like you can take some density of weight, I mean, not Solitons.
Yeah. Okay. Right. So because we were talking about free particles.
Yeah. Well, because you have this free transform. I mean,
yeah.
not free particles, a free field.
Right.
And this you don't have particles.
Okay. So what you can do is perform the same approach from finite gap, but so actually there are two limits that keep the density finite. There is this one, and there's another limit where instead of collapsing the bands to points, you collapse the gaps.
Yeah, so then that will be the.
And then, yes.
But it hasn't been written.
But so, what is the reason that you had to take this limit to Soliton?
Okay. So if you just take the Soliton limit and then increase n without keeping some relation between the size of the bands and the number of bands, either you end up with zero density. So if your band width is smaller than exponentially, you end up with zero density, and if you're bigger than exponential, you have infinite density.
But also, I mean, you have all of these bands, right? And then you're kind of setting them their band to zero and you're adding more bands. Right?
Yeah.
But I mean, there could be other ways of also in the end generating like some nice density of states. Right?
So yes, there is another way of doing this, but that's the limit I was mentioning to them. Instead of collapsing to points, the dense points, you collapsing the gas points. But if there's no other n-band limit with n goes to infinity that keeps the density finite.
Okay, then I think, sorry, we have to leave the class, but thank you very much.